Good afternoon, and very glad to be here to present our work guaranteeing deadlines for inter-data center transfers. And this is Hong from SynLab HKUST, and this is a joint work with Kai, Wei, Dongsu, Chen, Hao, Haibing, and Ming. We know that nowadays many big companies like Microsoft, Google, and Amazon distribute their data centers all around the world. And the inter-data center WAN connecting these data centers becomes very critical and expensive resources, which cost hundreds of millions of dollars every year. As a consequence, how to efficiently schedule traffic on inter-data center WANs becomes a problem of great importance. So an efficient traffic schedule should achieve high network utilization, which is the main focus of some previous works like B4 and SWAN. And on the other hand, an efficient traffic schedule should also achieve good QoS requirements for each individual transfers, which is a main concern of this paper. So based on the different QoS requirements, inter-data center traffic can be largely categorized into the following three classes. Interactive traffic refers to small flows which are most sensitive to delay. For example, a 100 milliseconds delay of interactive traffic may greatly degenerate user experience. And opposite to that, background traffic refers to those transfers without strict time requirement. And actually, a large amount of transfer lies between these two categories, which require delivery within certain time periods, usually tens of minutes to several hours. And in this paper, we refer to this category as large transfer. The observation is that large transfers are important because a large amount of interdata traffic actually lies in this category. The first example is content update. For instance, web search application wants to update and propagate a whole new index every 24 hours across its data centers. So missing such deadline reduces the response quality of the web search application. And the second example is about geo-replication. For instance, a web document application must geo-replicate user data every 2 hours so that only the changes in the most recent 2 hours could be lost due to a single data center outage. So missing such deadline degenerates the robustness of the document application system. So traffic scheduling should also take these QoS requirements into consideration. For interactive traffic, it should be delivered as soon as possible, so we can just give them the highest priority in the priority queues. For the background traffic, because it only needs best effort delivery, so we can just assign them with the lowest priority. But for large transfers, as the deadline requirements should be respected, and different transfers may have different deadlines and they come to the system at different time points. So fine-grained traffic scheduling is needed to respect all these deadlines. The question here is, are current solutions efficient enough to schedule these large transfers? To answer this question, we first investigate the inter-data center WAN rate control in public cloud nowadays. We did some experiments in the inter-data center WAN in AWS. And in the first experiment, we measured the inter-data center throughput variation from site to site by sending data from the data center in Virginia to different destination data centers. As we can see here in this chart, actually Amazon provides 3 different SLA types with respect to the network condition, low, moderate, and high. And even within the same type, we can see that the throughput varies a lot among different destination data centers. And in the second experiment, we also measure the inter-data center throughput variation from time to time. Here, the bandwidth ratio refers to the ratio between the highest and the lowest bandwidth on the same link over 35 hours. As we can see here, the variance is also very big, from 2 to 5. So based on these observations, we can infer that it is hard to guarantee deadlines in AWS inter-data center WAN due to its high variability. And for the current inter-data center traffic engineering techniques, such as B4 and SWAN, published in CCOM 13, their goals are mainly about how to achieve high network utilization while achieve high fair bandwidth sharing. So in another word, they are deadline agnostic. So because different transfers have different deadlines, so actually in this example we can see that fair sharing may lead to a lot more transfers to miss their deadlines compared to this optimal schedule shown on the right. So we can say that current inter-data center TE techniques do not guarantee deadlines. Another idea is to transfer deadline guarantees to a fixed bandwidth fixed bandwidth guarantee, and then just apply some intra-data center transfer guarantee, data center bandwidth guarantee solutions to enforce such guarantee. But the problem with this idea is that it could be quite insufficient in terms of the network utilization. We can take this example. And this is an inter-datacenter link with a capacity B, and the blue parts are the bandwidth taken or already reserved over different time slots. And now a request comes, and if we transfer this request into a bandwidth guarantee, it cannot be accepted. But actually, if we only consider the deadline constraint and do more flexible bandwidth allocation over different time slots, it can be accepted. So we can see that intra-data center bandwidth guarantee solutions are insufficient to ensure high network utilization. To conclude, most current solutions are insufficient when handling large transfers in this way or another. Basically, there are two reasons. The first, they lack an interface for users to specify their transfer deadlines. And second, they lack a mechanism to ensure the completion while achieving high network utilization. So to solve this problem, we first propose a very simple deadline-based abstraction, DNA. It just let the users to specify their deadlines, and it is more flexible than the bandwidth-based guarantees. And based on this abstraction, we design our deadline guaranteed data transfer system, Amoeba. It guarantees deadlines for large transfers while achieving high network utilization at the same time. So this is how our deadline-based abstraction looks like. And a transfer is characterized by this tuple, the source, the destination, the volume to be transferred Q, and the starting time of the transfer TS. And here we use two parameters, TD1 and TD2, to describe the deadline requirement of a request. To better explain it, we can consider the user deadline requirement as a utility function with respect to the finishing time. So if a request is finished, if a transfer is finished within time TD1, the user will suffer from no utility loss. And if it is finished after the time TD2, it will be totally meaningless to the user. So here, to be concise, we just take these two critical time points, TD1 and TD2, to represent the user deadline requirements. And as we can see here, we do not specify any bandwidth schedule here. So actually, a transfer can be satisfied by infinite many different kinds of bandwidth schedules. So it is more flexible than the bandwidth-based abstractions for scheduling. And we further define a request as a collection of correlated transfers with a unified deadline requirement. And next, we will introduce how the system Amoeba works in one slide. So basically, we have an Amoeba controller, which is in charge of admission control. And we have these side workers located in each data center, which is in charge of allocation enforcement and interactive traffic prediction. So when a request comes, it will just submit its request in the form of DNA to the controller. And the admission control algorithm will try to come up with a schedule which satisfies the requests by using the residual bandwidth left over by the interactive traffic, because interactive traffic has a higher priority. So the prediction and the interactive traffic is predicted and gathered by the interactive traffic prediction modular in the side workers. And if the request can be accepted, then the controller will just promise the tenant a guaranteed deadline, which is between the time TD1 and TD2, as we just mentioned. And it will just inform each side worker the bandwidth and routing schedule. And these schedules will be enforced by the allocation enforcement module. Here, because we are dealing with deadlines of tens of minutes to several hours long, so we just slide time into time slots of 5 minutes, and we do the scheduling in the granularity of this time slot. And in the next few slides, I'm going to talk about some details about Amoeba's design. First is how we design the admission control, and then some practical issues. The first admission control, it is done in a first-come, first-served manner without preemption on previous made deadline guarantees. So the first two algorithms comes to our mind as follows. The first algorithm is that for any new request, we assume all the previous request schedules are fixed, and we just do the allocation of the new request using the residual bandwidth. And the second one is that when a new request comes, we schedule all the previous requests without violating their deadlines. So the problem with the first algorithm is that it is quite suboptimal because actually these previous schedules can be modified as long as the deadline requirements are not violated. The problem with the second one is that it is too slow because rescheduling all the previous requests will just introduce too many variables and too many constraints. So here the problem is how to balance the scalability and the optimality of the algorithm. Considering this, we design the mission control as follows. So for a new request, we first try to find a schedule with a completion time t prime as early as possible, assuming all the previous decisions are fixed. So this is basically the first algorithm I just mentioned. And we refer to this step as adaptive scheduling. And if the resulted completion time t prime is smaller than td1, which means it is good enough, then we will just accept this request with this deadline. Otherwise, we will further try to reduce the completion time t prime to d double prime by rescheduling previous accepted requests in a cost-effective way. So we refer to this step as OR, opportunistic rescheduling. We will come back to this later. And if the resulted completion time t double prime is still larger than td2, then we will just reject this request because accepting it will just do no benefit to the user. Otherwise, we will just give the user a deadline, which is the best we can offer. So here, basically, there are 2 points. The first one is that we do this in a hierarchical way, so that for a lot of requests, actually, the rescheduling part, which is the most time-consuming part, may not be triggered. And second is that the rescheduling is done in a cost-effective way, which means we actually only select a small number of most relevant requests to do rescheduling, rather than reschedule all of them. And these 2 points makes our algorithm fast yet quite efficient. So in the next few slides, I'm going to talk about these 2 components. First, the adaptive scheduling AS is basically an optimization problem. So given the topology and given the request and given all the residual bandwidths on the links over different time slots, we first build this temporal expanded graph, which describing all these constraints. On this graph, it is more straightforward to do the routing and the rate control, rate scheduling over different time slots, considering all the correlations. And based on this graph, we formulate the problem of finding the shortest possible completion time as a mean cost flow problem, which can be easily solved by any LP solvers. And the opportunistic rescheduling actually based on these 2 heuristics, local stretching and joint rescheduling. The idea of local stretching is quite simple. On all the congested passes, we try to shift the bandwidth schedules of the previous requests out of the time window of the new request. So as we can see in this simple example, D is a new request, and we just try to shift the old request A, B, C out of the desired time window of the old request, of the new request. So the new request will have a bigger chance to be allocated. So if it doesn't work, so we will further trigger joint rescheduling. So the idea is as follows. For the new request, we first try to score the helpness of previous requests. So this helpness of our old request means to what extent will the reschedule of this old request help to accept the new request. And the measurement of helpness is based on two heuristics. The details please refer to the paper. And after we do this scoring for all requests, then we just schedule the new request together with the k previous ones with highest scores. And the reschedule, this procedure is done in a similar way as in AS, adaptive scheduling. And the constraints are that the previous allocations do not violate their deadlines. And the goal is that to minimize completion time of the new request. So next we will talk about some practical issues. First is enforcement. Second is interactive traffic prediction. So the routing enforcement is done by leveraging explicit routing path control. So this is actually XPath is another work done by our group, which will be presented in the upcoming NSDI. And the bandwidth enforcement is done by using Linux TC modular at endhost to do rate limiting. And it's worth mentioning that Amoeba can be readily deployed today because it requires no changes to tenant applications. It requires no modifications on network devices. And in our prototype experiment, we find that it only introduces only 3% of CPU overhead at endhost. And as for interactive traffic prediction, the good news is that interactive traffic only accounts for 5 to 50% of the total traffic. And also, although interactive traffic may surge within a very short time period, the average volume over a 5 minutes window is relatively stable and can be largely predicted. So remember that we're doing the scheduling in a granularity of 5 minutes. So here to deal with interactive traffic misprediction, we just set extra headroom based on the predicted volume, the predicted rate. And to deal with the interactive traffic surge within a small time period, we just borrow bandwidth from deadline transfers and return them in the future. And we try to evaluate our design by using the following simulation setup. We consider two topologies, G-scale of Google and IDN of Microsoft. As for the workload, interactive traffic is randomly generated with a total demand from 5 to 50%. And for large transfer, the arrival is simulated as a Poisson process, and the deadline volume and the volume are simulated following exponential distribution. And we focus on the following performance metrics: the result acceptance and rejection rate, and the network utilization and throughput. So here we just select some experiment results, or simulation results. First, we compare Amoeba with the fixed bandwidth guarantee solution we just mentioned in the motivation part. We can see that Amoeba satisfies up to 50% more requests, and it achieves up to 60% higher throughput. And we also compare Amoeba with the existing TE techniques, such as Wang and Teacher, which is another TE paper. And we find that Amoeba accommodates up to 16 more requests to finish within their deadlines while achieving a comparable throughput. And as we have mentioned that we try to strike a good balance between scalability and optimality. And so here we design this evaluation between Amoeba and the global optimization algorithm, which greatly just reschedule all the previous requests. Here we find that Amoeba achieves 30 times speed up while sacrificing only around 3% of network utilization. To validate our design, to validate the simulation results, we build our prototype using 13 servers and 6 switches to emulate an inter-datacenter WAN with 6 data centers. And the first observation is that the scheduled volume and the measured rate and the measured completion time are highly consistent with the scheduled volume and the scheduled completion time, which means that we achieve a very accurate real-time enforcement. And the second observation is that because we do the same experiment as we did in the simulation, and we find that the results are highly consistent with the simulation results. Finally, to conclude the paper, in this paper, we point out the problem is that a large portion of inter-datacenter transfers have deadlines. However, currently, no mechanism is in place to ensure such deadlines. So to solve this problem, we first propose such deadline-based abstraction DNA, which let users to specify their deadlines, and which is more flexible than bandwidth-based abstractions. And then based on this abstraction, we propose our deadline guaranteed data transfer system, Amoeba. It guarantees deadlines for large transfers and while achieving high network utilization at the same time. So that's all. Thanks, and ready for questions.
Thank you for the talk. I just have a small question. Maybe I missed it during the presentation. Similar work has been done within the cluster, the jockey deadline.
Okay.
But that was within the cluster, within the data center. And I saw similarities in the solution. Did you, have you done any tweak to adapt it for inter-datacenter data transfer?
Just
a simple comparison between yours and Jockey, although I know the context is different.
Yeah, we didn't do the comparison. Actually, I ran through that paper, but I didn't look into detail, but actually I think the Jockey paper is the deadline is about the computation time and the transmission time. They're coupled, but here we only consider the transfer time.
Transfer.
So,
okay, thank you.
and the algorithms are also different, right?
Okay.
Thank you. Steve Han, Google. I'm just wondering, have you thought about trying to extend this to coordinating multiple related transfers? Perhaps using, for when you're trying to get multiple replicas, you mentioned georeplication, you actually care about, compound primitives rather than a single deadline for a single transfer?
You mean some sequencing okay, I think that's a very good.
There was some work on a thing called logistical networking a number of years ago that they used for data transfer coordination for big data. The scientists, it's FTP, right? So
okay.
You can do better than that. But I just thought it reminded me a little bit of your work. It might be worth looking at.
Yeah, thank you. Thank you for the suggestion.
Following on from my previous talk, under what circumstances does this not work well?
Sorry, I didn't.
Under what circumstances does this not work well? I like the fact that it does in your evaluation, but what about the corner cases? What would trigger them?
Oh, okay, let me think. You mean it doesn't work well means it it is not optimized or it have some other problems?
You tell me.
Okay. I think in some for some, maybe in sometimes the prediction may not be of the interactive traffic may not be very accurate, so we have to give up some accepted requests, and this is one. And also, I think maybe when the request arrival rate is very high, then we have to further reduce the computation time to accept each one new request. So that's maybe some bad parts of something we can modify.